A universe that never truly begins or ends, but keeps looping through time in infinite cycles. The universe starts with a big bang, expanding and creating everything we know, but instead of expanding forever, it eventually stops and contracts, leading to a big crunch. This cycle repeats indefinitely, creating a series of endless bounces. Even Albert Einstein toyed with the concept back in 1930. He imagined a universe that would expand and contract, bouncing back with every big bang and big crunch. It's almost like the universe has its own heartbeat, pulsing through time. But how does this work? Well, one theory suggests that during the expansion phase, the universe spreads out, galaxies drift apart, stars burn out. Eventually, gravity pulls everything back together, leading to a colossal collapse. When everything gets compressed to a singular point, another Big Bang ignites, starting the process all over again. Now, you might be wondering, why don't we see evidence of previous cycles? That's a great question. Some scientists believe that the transition between cycles might erase the evidence of earlier universes. Let's take a closer look at a specific model that has captivated scientists, the Steinhardt-Turok model. This model, also known as the ekpyrotic universe, proposes an even more intricate dance of cosmic events. Imagine two parallel orbifold planes, or M-branes, that collide periodically in a higher dimensional space. Our visible four-dimensional universe lies on one of these branes. These colossal collisions correspond to a reversal from contraction to expansion, essentially a big crunch followed immediately by a big bang. The matter and radiation we see today were generated during the most recent collision, in a pattern dictated by quantum fluctuations created before the branes. After billions of years, the universe reached the state we observe today. After additional billions of years, it will ultimately begin to contract again. However, this model isn't without its challenges. Earlier cyclic models failed because the universe would undergo inevitable thermodynamic heat death. The newer cyclic model evades this by having a net expansion each cycle, preventing entropy from building up. Yet there remain major open issues. Colliding branes are not well understood by string theorists, and there's uncertainty about whether the scale invariant spectrum will be destroyed by the Big Crunch. And similar to cosmic inflation, while the general character of the forces required to create vacuum fluctuations is known, there is no candidate from particle physics. Next, we have the Baum-Frampton model, proposed in 2007. This model introduces an exotic form of dark energy known as phantom energy, which possesses negative kinetic energy and would typically lead to a catastrophic event known as the Big Rip. The Big Rip occurs when the universe's expansion accelerates so rapidly that it ultimately tears apart all matter down to the atomic level. However, the Baum-Frampton model offers a fascinating twist. In this instant, only one causal patch of the universe is retained, and it contains no quarks, leptons, or force carriers, only dark energy, causing its entropy to vanish. This much smaller, empty universe then undergoes an adiabatic contraction with constant vanishing entropy, avoiding complications like black holes and excessive structure formation. The condition of having WBU, the cosmological equation of state parameter, less than -1, is logically inevitable in a truly infinitely cyclic cosmology because of the entropy problem. Despite its elegance, the Baum-Frampton model still requires extensive technical calculations to confirm its consistency. Next theory is conformal cyclic cosmology, proposed by Roger Penrose. This general relativity-based theory suggests that the universe expands until all matter decays into light, resulting in a state where time and distance scales become irrelevant. In this scenario, the universe effectively resets, becoming identical to the Big Bang and initiating a new cycle. Another compelling model is loop quantum cosmology. This theory predicts a quantum bridge that connects contracting and expanding phases of the universe. Essentially, it suggests that the universe undergoes a quantum bounce rather than a classical big crunch, providing a seamless transition between cycles. Then there's Gorkovy's no dark matter and energy model. Recent discoveries in observational astrophysics and cosmology have allowed us to consider a universe without exotic dark matter and dark energy. According to Nikolai Gorkovych's work, each cycle begins with expansion driven by anti-gravity forces. This occurs as a result of a decrease in the system's mass during black hole mergers, where about 5% of the total mass converts into energy through gravitational wave. Conversely, compression happens due to the predominance of gravitational forces, which increase as black holes grow by absorbing gravitational waves. In the 1920s, theoretical physicists, most notably Albert Einstein, considered the possibility of a cyclic model for the universe as an everlasting alternative to the model of an expanding universe. In 1922, Alexander Friedmann introduced the oscillating universe theory. However, work by Richard C. Tolman in 1934 showed that these early attempts failed because of the cyclic problem. According to the second law of thermodynamics, entropy can only increase. This implies that successive cycles grow longer and larger. Extrapolating back in time, cycles before the present one become shorter and smaller, culminating again in a big bang, and thus not replacing it. This puzzling situation remained for many decades until the early 21st century, when the recently discovered dark energy component provided new hope for a consistent cyclic cosmology. In 2011, a 5-year survey of 200,000 galaxies and spanning 7 billion years of cosmic time confirmed that dark energy is driving our universe apart at accelerating speeds. One new cyclic model is the brain cosmology model of the creation of the universe, derived from the earlier ekpyrotic model. It was proposed in 2001 by Paul Steinhardt of Princeton University and Neil Turok of Cambridge University. The theory describes a universe exploding into existence not just once, but repeatedly over time. The theory could potentially explain why a repulsive form of energy known as the cosmological constant, which is accelerating the expansion of the universe, is several orders of magnitude smaller than predicted by the standard Big Bang model. A different cyclic model relying on the notion of phantom energy was proposed in 2007 by Loris Baum and Paul Frampton of the University of North Carolina at Chapel Hill. Other cyclic models include conformal cyclic cosmology and loop quantum cosmology. In conclusion, the cyclic model, universe's endless cycles of birth, death, and rebirth. From the ekpyrotic universe to the Baum-Frampton model, each theory provides unique insights into the nature of our cosmos. But what lies ahead for cyclic cosmology? With the advent of new technologies and advanced observational tools, scientists are now able to probe deeper into the mysteries of the universe than ever before. The next generation of space telescopes, gravitational wave detectors, and particle accelerators promises to bring unprecedented clarity to our understanding of cosmic cycles. Moreover, interdisciplinary research bridging quantum mechanics, string theory, and general relativity could unlock new dimensions of knowledge, offering fresh insights into the very fabric of space and time.